already asked that? Okay. Well, I'm glad. All right, so we'll see how much we can get through for this section. And this is our, you notice the pattern of this book. It kind of takes the last section, wraps everything up we talked about for that chapter in an application package. And that's kind of what we're going to be doing with this stuff today. So taking all of the domain and range and inverse and functions and quadratics and applying them to some application problems. You're going to see the importance of function notation and why we use it. So these first two examples we're going to do are kind of a little abstract, not so much application, but just kind of getting us to try and think about a process, see if we can understand the concept of this whole thinking of writing a function notation involving one variable. Because if I had multiple variables within a certain situation, it's nice to eliminate as many variables as possible so that you can simplify your work instructions. And sometimes eliminating a variable simply means rewriting for another variable. We can take an equation that we do know and solve it for another variable that we can then plug into a different equation. So that's what we're going to be doing with this stuff today. Area of a circle, circumference of a circle. We probably remember what those are, right? You guys remember those formulas? Yes? Uh-oh. Okay, what are they? What's the area of a circle? Okay, area of a circle, pi r squared. What is the circumference? 2 pi r. All right. So you'll notice in these two examples here that both of those equations have different variables, a and r, or c and r.
It's kind of like a law.
No way. What's kind of like a law?
Like you're like, oh, pi, bring it over, put the 2, hold 3 from, and then it's like, oh, it's something. Then you get it, do it.
Did you ever follow that?
Do my circle thing. We're on the area right now.
What am I doing?
Do the little loop-de-loop.
Do the loop-de-loop.
Got the pi. No, not pi. Go to the pi.
Go to the pi.
Go lower on bottom of it. Go to the 2.
Go to the 2.
And then the 2 to the r.
2 to the r.
Wait, no.
Okay. Alright. Anyway. Okay. Let's see if we can get this going. So we want to express area as a function of circumference. And what that means is we want to express A of C. But then we also want to do circumference as a function of area. So C of A. All right, so what does that mean? What does A of C mean? Well, right now, this blue equation, the little O is just a circle. That's all it means, area of a circle. So in this little, in this blue equation, this is actually calculating the area in terms of an R. This is the same thing as saying A of R is equal to pi r squared. This is function notation, area as a function of radius, and this is just our generic formula. But they mean the same thing. One of them is just function notation, telling me how I find area. I find area by plugging in an R, a value of R. Pi is a constant, I don't need to worry about that. Circumference equals 2 pi r. This is a circumference equation in terms of radius. So there's the function notation for this one. A of r using radius, C of r using radius. What we want to do is find A of C. So I'd like to replace all of my unknowns, which are right now r's, I would like to replace them with c. All right, so that's our goal. See if we can rewrite these things. So if I'm going to do that, if I'm going to replace this radius with a circumference, then that probably means we should start tweaking the circumference equation first. Because if I tweak the circumference equation, then I can plug that into the area equation and come up with area as in terms of the circumference. So what are we doing? Let's do this. Let's take circumference right now. And well, notice first of all that both the equations have r's in them. Pi r squared or 2 pi r. Which means if I could replace in the area equation, if I could replace r with a c, that would be wonderful. Then I have a of c instead of a of r. So in order for us to replace this r with a c, we need to take our circumference equation and solve it for r. And if we did that, we have radius is equal circumference over 2 pi. Why am I solving for r again? Because r is the variable in the area equation that I want to replace. I want to replace it. And it looks like I'm going to be replacing it with c over 2 pi. So now this, our a of r is really now an a of c over 2 pi. And I get pi r squared. Simplify this, and we get area as a function of circumference. Pi c squared over 4 pi squared. Pi on the top cancels with one of the pi's at the bottom. And we get the area as a function of circumference is equal to c squared over 4 pi. And there we go. What? All we did was we rewrote an equation that we're familiar with, and we rewrote it in terms of a different variable. That's it. So now, if I had information given in a problem that told me circumference, didn't give me any information related to radius, I can now use this equation to find the area. What do you think? Two equations to work with. Pick one of them. Solve for the variable of the other equation that we want to replace. Plugged it in there and came up with an area in terms of a new variable. A little abstract, huh? Just rewriting equations is what we're doing there. All right, what about circumference as now a function of area instead of circumference as a function of radius? What do you think I should do to start this problem?
Solve r for AO.
There you go. So I want to replace all the radius values in circumference now with an a. So we're going to go take our area equation. We're going to use area equal pi r squared, and we're going to solve for r. Just like we did on the other problem. Why? Because the circumference equation has 2 pi r in it, and we're going to replace that r. Let's make these all move, shall we? Doing red. What's my problem? All right. So now we're going to go and we're going to replace. So we have c. So normally our c as a function of radius is equal to 2 pi r. But we're going to solve area in terms of radius. R squared would equal a over pi. And then we would take the square root and we get the square root of a over the square root of pi. And if we we're solving a equals pi r squared. We're solving for r squared. Divide by pi. Then we take the square root to undo square. So I've got square root of a over pi, which I just separated it into square root of a over square root of pi. Then we rationalize the denominator. We don't want radicals down there. We had to multiply the top and bottom by the square root of pi. And we ended up with that. You guys hanging on? Are you alright? Am I going too fast? Yes.
For that one, how is AC equal to pi c squared over 4 pi squared?
Okay, so how does what?
AC, how does AC equal pi c squared 4 pi squared? How do you come up with that?
Oh, okay. How did we go to there?
Yeah.
Alright. So I'm replacing r with c over 2 pi.
Yeah.
So I take my area equation, which is normally pi r squared, and I'm replacing r with c over 2 pi. Then I square c, get c squared. I square 2 pi, get 4 pi squared. Pi's on top cancels one of the pi's on the bottom, and I end up with c squared.
What would be the AC?
What AC are you talking about?
The one in the middle.
This one?
Yeah.
I'm just replacing r with this.
The one underneath.
Look, here's what r is now.
I thought the one underneath it.
This one?
Yeah.
Oh. Okay, we did this bit to solve for area as a function of circumference. So that's all that this just means area as a function of circumference. Because there's no more r's in the equation, right? So instead of a of r's, it's now a of c's. That's my only variable.
Okay.
Yeah. Right. Let's go back over here to the red one. So I now have r in terms of a. We're going to replace that r with our r in the circumference. So now I'm doing this. I want to take c of r is going to become c of a pi over pi. And that will become 2 pi times root a pi over pi. So far, so good?
Hey, why is there two?
Why is there 2 where?
A two by r.
2 pi r. And we're replacing that r with a pi over pi.
You just looked at it.
No, I can simplify that, can't I? Yeah, so we'd have to simplify this, and we get circumference as a function of area is equal to, pi's cancel, 2 root a pi. So we've changed our normal, yeah, I guess we call it normal. We changed our, maybe not normal, our equations that we're most familiar with, area, circumference, which were originally expressed in terms of a radius. We've changed them to become expressed in terms of a different variable. That's all we're doing. What do you think? Is that horrible? What part's horrible?
Well, I understand it, it's just a lot of process.
Oh, okay. That's okay. We're going to have plenty of time to play with it because that's all that we're going to be doing with this section is finding a function, finding another function, and then tweaking one of them to plug into it. That's all we're going to be doing. Placing a different variable.
Are you going to give us word problems?
Yes. We're going to have some applications.
Ew.
Okay, here's another abstractor. So we got to get a little visual going on for this one. Maybe I'll let you read it for a second so you can kind of understand what it is we're supposed to be finding. All right, think you got it? Got an idea what we're doing? Somebody help explain in your own words what we're going to be doing with this? Like for part A, what do we do? Oh, maybe we need to back up even further then, huh? Point P, given some coordinate x, y. We don't know what it is. Arbitrary point that is on the line, x minus 3y equals 5. So here's our line, x minus 3y equals 5, the purple line there. And there is a point residing somewhere on that purple line right now. That's what we've got. Okay? Somewhere on that purple line we've got some point. For part A, it wants to know specifically what is the distance d from the origin to that point as a function of the y coordinate. All right. So we want to go the distance from the origin to some arbitrary point. All right, let's pick an arbitrary point. Let's say we're going right there. I'm not picking some nice, easy point. We're just going to say there's our arbitrary point. And right now that point has some coordinate x, y. And we're supposed to find the distance from the origin out to that point. So we're supposed to find this distance in respect or with respect to the y coordinate of that point, which means I don't want any x's. In our distance formula, we have x's. Oh no. What, pray tell, shall we do? All right, so here we go. We know that distance of something is equal to x2 minus x1 squared plus y2 minus y1 squared. So that's just the difference in x's, the difference in y's. We square them out together. That's our distance formula. Now, in this setup, this is in terms of x and y. So in terms of a function notation, this is a two-variable function. D of x and y is equal to blah, 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 blah. Why? Because I have x's and y's in the equation. We want this to become a d of just y. Well, let's simplify this just a little bit more. If we're using 0, 0, what this can become, the distance of x, y, can now become the square root of x minus 0 squared, or x squared, plus y minus 0 squared, or y squared. Because we're referring to the origin 0, 0 as my y1s and my x1s. So we replace x1 and y1 with 0, and we get that. Is everybody okay so far? Am I going too fast? Just slow me down. Okay. So we need to change this x so that it becomes a y. So that I can now write distance as a function of the y values only, no more x's. How are we going to do that? How are we going to change our x's to become y's so that I can use y's? No ideas, huh? Oh, there's an idea. I like ideas. Go ahead.
You take the equation of the line, solve it for x, or solve it for something and substitute that.
Great idea. Did you guys catch that? Take the equation of our line, x minus 3y equals 5. Solve it for, what are we going to solve for, x or y? Good. We're going to solve for x because we want to replace x's with y's. So we solve it for x, and we get x is equal to 3y plus 5. And then now that becomes the x coordinate that I need to plug in down here in my distance formula. So now this becomes 3, what was it, 3x plus, 3y plus 5 There's my x squared plus y squared. Okay, let's go back and kind of, again, highlight why we can do this. Why are we able to say that that is the x coordinate of this point? Well, in any equation, not just a linear one. If I have an equation that has variables x and y's, and I solve for either x or y, and I pick a value of the other variable, let's say I pick the value for y, I put a 1 in there for y, I get 3 plus 5, I get 8, x is equal to 8, y is equal to 1, I found a pair. I found an ordered pair that is on that line. So you can always solve an equation for one of the variables, and that's the same thing as saying that is your coordinate for that particular variable. We're just not seeing it, we're used to seeing it as an ordered pair like number. Well, and it's just an expression now in terms of y's and x. So if I were to write that as an ordered pair for this particular point, that would be my x value, 3y plus 5. My y value would be x minus 5 divided by 3. There's the y part of that. All right, let's solve that for y. All right. Are we okay so far?
Yeah.
Oh, you need to see in the back there? Here we go. So we have some work to do here underneath the radical. We got some foiling. We get a 9y squared plus a 30y plus a 25 plus a y squared. I'm foiling all that 3y plus 5 stuff out. Combining all my like terms, my y squareds combined, and I finally get my answer for part A. That the distance as a function of y values only is equal to the root of 10y squared plus 30y plus 1. There's the answer for part A. All right, again, just distance to some arbitrary point. There it is. Yes,
So we need to find a d of x.
pardon me?
We need to find a d of x.
Okay, how come we didn't find the d of x? Because it said to find the distance as a function of the y coordinates. Right there. If it said find a distance as a function of the x coordinate, then what would I have done differently?
Just plug in that.
I would have plugged in, I solved for y's, plug in those for the y values, and I have everything in terms of x's. All right, now we get part B. Now we want to know the hint, minimum distance d, and the value of some point that is associated with this minimum distance. So let's think about, yes ma'am?
In the equation for example, it's function of y squared.
9y squared plus 30y plus 25 plus y squared. Okay, so now here's what the picture is. Now I want specifically the shortest distance to any point on this line from the origin. Where does that have to go? Yes. Oh. Sorry, didn't mean to get upset. Where does that have to go? How do I have to connect to that line if I'm going to be the shortest distance? Perpendicular, very good. Perpendicular bisector, or not necessarily bisector, but a perpendicular connection, right there. That is going to be the point I'm interested in, because that's going to be the shortest distance to the line from the origin. Okay, so we got to go find that coordinate, whatever that coordinate is. But we also have to find what's that distance. So there are two ways to do this. Anyone think of one way we can do this? Yes?
Or do you just set them equal to each other?
Okay, that'd be great if I knew what.
If you need the equation of the origin.
You mean the equation of the blue line?
Yes.
Yes, if I knew the equation of the blue line, I could set that equation along with the equation of the purple line, which we already know. I can find out the ordered pair intersection from doing that. How do I find the equation of the blue line? Bingo. So I could find the slope of the purple line. take that slope, make it an opposite reciprocal, find now the slope of the blue line going through 0, 0, and I can find the equation of that blue line. And then I can set the two equal to each other and do what you just said. Go find out their intersection. Right? That's one way I can do that. There is another one. And it has to do, we're going to peek now at our distance as a function of y, but we're going to focus in on that part of this distance function. That 10y squared 30y 25 piece. And then we've got this word here. What am I going to do with the quadratic and the word minimum?
So find the vertex.
Find my axis of symmetry and then find my vertex. Exactly. So because I can pull this piece out of this radicand here, that has to be, a minimum has to occur at the axis of symmetry of this quadratic. That means y is equal to negative b over 2a, or negative 30 over 2 times 10, or negative 3 halves. That is the y value that will minimize this distance. So right now in my coordinate, I know that this is negative 3 halves. How do I go find the x? I plug it in where? Good. I plug it into the original equation of my line, right? I want to find that's the point on my purple line, so I'm going to use the x minus 3y equal 5. And we're going to go find the x. Say that again. Good question. Why am I doing it to the original? Because is that a point that's on the purple line? It is. If it's a point on the line, I get to use the equation. All right, and we say that x minus 3 times negative 3 halves is equal to 5. So x plus 9 halves equal to 10 halves. So x must equal 1 half. There we go. We've answered part of question B. We found the point where they intersect. So we were asked also to find out, I think, what is the distance? Well, we're going to use this negative 3 halves now, since that's the value of y that's going to minimize. That will also be the value of y that makes my distance the smallest. So now I'm going to plug that baby back into here. Negative 3 halves squared, 30 times negative 3 halves, and 25. And we go and we calculate all this to get 10 times 9/4, which is actually 94, but we can divide the 10. Oh, here. Da-da-da-da. I'm going to make everything halves. So here, 4, 5, right, come out of that thing. This is still all under the square root. So we have 45 halves minus 90 halves, which is negative 45 halves, plus 50 halves gives me the square root of 5 halves, which is, I don't know, what's the square root of 2.5? 1.6? 1 point what? 1.8?
Oh, sorry, 1.5.
1.5.
Yeah.
All right. 1.58. There's the distance. That's how long that line is. Units, we don't know what the units are. But that's how long the line is that connects the origin to the purple. 1.58, whatever. Units. All right. Now we get to the even more abstract component of this. Part C. But before we go to part C, are there any questions on A or B? All right. All right. So let's see what this thing looks like. this distance is a function of y formula. Now I'm plotting it as an x, y thing. I'm going to pull this up here. Here's what that actually looks like. Kind of looks like a parabola. It has a little bit of a flatter bottom. We can't see it because we're zoomed out. But if I were to zoom in on the vertex area of that thing, you notice how it's more kind of V-shaped than it is U-shaped. That's because I'm under that root. So this is not our traditional radical function. I just can't think of a parent for this one because I've got a quadratic. And I'm thinking about what's underneath quadratic-wise in terms of a domain for that thing. What are parabola's domains always? Yeah, they're all reals. Yep, everything works here. So we think about the domain of this red function, this radical of 10x squared plus 30x plus 25. What does it look like the domain of that thing is? Of the red graph. It looks like it's all reals to me too, yeah. I think everything works there. I can put any value of x in or y into this thing, negatives, positives, 0, and I'll get always a positive solution. So it's easier to think about this, you see the graph, and yes, you wouldn't know that that's a parent. Parent graphs, you have to want to graph. Darn it. All right, so we check the graph. Of this guy. And we see that in terms of its domain, we would have, now we're talking about distance as a function of y. So my domain values are actually these y values. So I'd say for the domain I'd have y such that y is all reals. Range-wise, go back and take a peek. What's the range have to be for that red one? Yeah, exactly. It needs to be greater than or equal to whatever that minimum value is, right? So we got to go find out what is that minimum y value associated with this. And we're going to say everything bigger than that. So we already know that the minimum occurs at a y equal of negative 3/2. Is that right? Is that what we had before? Yeah, negative 3/2. So we're going to go put that in. Oh, I already found it. Yeah. 1.5. So we know that we're going to be, in terms of our range, d of y such that d of y is having to be greater than or equal to 1. So that would be the range. You can get away with not having to look at the radical component of it. You can get away with just looking at what's underneath. That's a parabola. All reals for parabola in terms of domain value, and then plugging that value of x back in, but then taking the root of it because the root deals with d of y, not just y. So domain you can get away with simply looking at the radicand, but can't do that with the range. You gotta actually plug it in. Yeah.
I don't understand how you got domain range.
Okay. Are you cool with seeing the graph there?
Yeah, that's right.
All right. So that graph came from that equation. Okay. Graphically speaking, do you have a problem with seeing domain and range? Everything works for domain. My graph keeps going on and on, all values of x. Range values, it has a low point, so from that point and up is all of its range values, correct?
Yeah.
Okay, so graphically speaking, you can see the answer. All right? All we're doing down here is doing the algebra form.
How does y equal all reals thing when you said that there's a minimum value for that?
Okay, hang on. Notice that these y values are actually, quote, x values, right? Because we're talking domain is in terms of y's, because this is a d of y function, not a d of x function.
Oh,
So that's why it's saying y values are greater than or equal to reals for this thing. Okay? And the answer to your question of why it's all reals, two things. One, graphically we saw that. Two, the radicand, 10x squared plus 30x plus 25 is a parabola. And the domain of every parabola is all reals.
Okay.
That make sense?
And for the range, same thing.
Yeah, so range though, I'm looking at, because I'm asked to find the range of the distance as a function of y function. So once I find out what this minimum is, which we said was -3 halves, then we plug that back in, and then we found out that the vertex y value, so to speak, for this parabola would have been 1.58. So everything is opening up above the 1.58. Does that make sense there? I had to take the square root. All right, so that again, that's a little abstract. That was a tough one. But I hope maybe we can see some relationship between functions and we're plugging into other functions and writing function notation in terms of something else. Maybe. All righty. Let's get to a little bit more, I don't know if it's more practical, but different example, and then we'll probably wrap up with this one. All right, is that okay? Of course it is. We always have a dissenter in the group. They're depressing? That's not beige, it's actually supposed to be a pink.
I don't like it.
Yeah, I know, the videos, they chunk it. I know, it's weird, huh? Yeah, sorry about that. Would you rather me to have a white background?
No, I don't think it's neon green.
Oh, neon green, well, okay. Take care of that for you. Let's see. Bam! Woo! Is that better for you? Okay, whatever. Too bad we ain't sticking with it. I'll do that in the next one. How about that? I'll make all our next ones neon greeners. Okay. All right, so here, you're going to have a couple different of these types of problems. Sketching the little diagrams is going to be vitally important. This one, for example, we start at the same point. You're going to have others, though, where you might be starting at a point, moving away from it. And then 90 degrees away from the point, coming towards it. And you're going to find out some information related to these rate problems after so many seconds or minutes, right? Or something like that. So it's important that we understand the diagram. To understand the diagram, we need to do a very quick lesson on vectors. You guys, are you familiar with vectors?
Yeah.
Has anyone heard of the term vector before? Zach has. Can you briefly describe a vector, Zach? What's a vector? Okay, what symbol do we use for a vector? An arrow. We use an arrow to reference. So here's what a vector is. A vector. You guys are in physics. Well, you guys know. You guys know vector. Come on, vector from like yeah, Despicable Me.
Oh.
Yes, that vector. You know, so magnitude and direction. We have that movie at home. We watch it a lot. All right, shows both magnitude and direction.
Now I'm definitely plan on not saying it.
Whatever. You're gonna go home and watch it. All right, so magnitude. You've never seen Despicable Me? It's a great movie.
It's such a good movie.
Magnitude can represent force, if you're talking physics type problems, force. In this case, we're talking magnitude as a length. And then direction is obviously number of degrees if you're in a polar world, something like that. Or if you're talking about navigation, you're going to be using bearings. All right? So the vectors show magnitude and direction, and they're represented by an arrow that has a tail and a head. So the length of the arrow shows you magnitude, how long the arrow is can relate to the length or the force. The way the arrow is turned on an angle would indicate the direction of the vector. So we're going to use this and use vectors to draw this thing and see what happens. So first of all, I've got a rate, 6 meters per second. I've got another rate, 8 meters per second. And we need to remember this, that when we talk about rate problems that involve distance, distance is equal to rate times time. D is equal to RT, right? So here's what we've got. We've got a runner. Runner starts at point O. And one of them heads north, running at 6 meters a second. We have 6 meters per second going north. Now we have another runner heading east, and that runner is going 8 meters per second. So their vector is drawn a little longer because the magnitude is bigger. We're going 8 meters per second. And then after some time, we don't know what that time is, they are this far away from each other. We're going to call that distance as a function of time because we don't know how long they've been running. I just know that they've been running as a function of time. Okay, so if I have this triangle, and it's a nice triangle because it's a right triangle because I had north and east, I need to have all of the parts of that triangle be the same type of units. They all have to be rates, or they all have to be distance, or they all have to be time. Well, we've been asked to find a distance, so I would love for these things to become d of t's instead of r's or t's. So my question to you is this. Do I have, with that and that, a distance, yes or no?
No.
What do I need to put with those to make it become a distance? T. I need them to become T. This is just the R. These are just rates. So what I've got is I've got that part of a distance formula. I need to tack on the T to make it become a D. So it's pretty simple. We just now make this become 6T and 8T. Now I have distance. 6 meters per second times the number of seconds, meters. 8 meters per second times the number of seconds, meters. Now you have distance. So now I have everything ready to set up distance formula or Pythagoras theorem, right? A squared, B squared, C squared, right triangle. So I could find D of T. We would say that 6T squared plus 8T squared is equal to D of T squared. But we take the square root of all this stuff. Let's look for D of T. So D of T would equal the square root of 36T squared plus 64T squared. Simplifies to 100T squared. And now because that's a product, I can take the square root of these factors and get 100, which is 10, root of 100 is 10, and t, which is the square root of t squared, and get the d of t is equal to 10t. There it is. There's how far apart they are after t seconds. And again, we don't know what the units are, so we're just going to write d of t. So if you assume that the runners continue, they maintain their speeds, 6 meters per second, 8 meters per second, and they run for however long. Could you find how far apart they are at any given point in time?
Oh, yeah.
Yeah. Assuming you are maintaining your constant speed, constant velocity. Yes.
North and south.
Yeah. Oh, good question. So what if one was going north and one was going south? My distance would then be adding 8t and 6t together. It's no longer a triangle, so then I just simply am adding my vector lengths. Yeah. Good question. Yeah.
Do they have a problem for going south and south?
Yeah, we will eventually have problems where these vectors go off at something other than 90 degrees. And by that time, we'll have learned how to deal with lob sines and lob cosines, which are other ways for me to solve triangles that are not. Eventually, that's the second half. All right, so we'll stop it here. And we'll wrap up tomorrow with the next 2 or 3 slides. 3 more, I think. So this will just be the day 1 stuff.